Algebra. All right, you guys. 9.1 homework, simplifying radical expressions. I figured I'd just go over a couple problems that are good examples for the rest of the problems you'll be dealing with in this section. So I decided on 20 and 59, and I'm going to point out something in a couple of the other problems to make sure that you see it. Let's start with number 20 right here. So here's 20, and remember, I'm trying my best to write on this little thing here, it's a little pad, whatever it's called. It doesn't work very well, so please forgive me if it looks pretty bad. Okay, this says to simplify the square root of 48n to the fifth. Okay, so square root, first we write out the expression exactly as it is, 48n to the fifth power. Okay, now let's think about this. First of all, there's multiplication going on between 48 and n to the fifth. So we know that we can use the product property of square roots, because this is a square root without anything here. So the fact is, I can already write this as the square root of 48 times the square root of n to the fifth. Now, if I were showing work on my own, I would probably do two steps in one here, but this is just showing you first. Let's break this apart into two factors based on the product property of square roots. Now, the harder part. Can you take the square root of 48? And the answer is no, you can't take the square root of 48. But, as I mentioned in the videos and on Friday, what we can take the square root of are certain factors of 48. And what we want is a perfect squared factor of 48. So that way we can take the square root of it using the product property of square roots. Now, the perfect squares. 0 squared is 0, 1 squared is 1, 2 squared is 4. And you might go, oh, there it is, 4. What I'm going to show you is two alternate realities. All right, we're going to do the first reality where we use 4, and that would be 4 times 12. Okay, this is the first reality. And then this n to the fifth, we're going to get to it. I'm just going to leave a little blank right here. We'll get to that later. But we break this into square root of 4 times 12. Okay, so then I can use the product property of square roots again. I take the square root of 4 times the square root of 12. And I get 2 root 12. And you might be like, okay, cool, I've dealt with the square root of 48 issue. If you do the square root of n to the fifth correctly here and you get this factor, you're going to type this into big IDs and it's going to say it's wrong. And here's why it's going to say it's wrong. Because 12 also has a factor of 4 and therefore also has a perfect squared factor. So you can keep going here to 4 times 3 to represent 12. And then using the product property of square roots. I know I'm showing every single step, but that's because I'm not right in front of you to be able to say, hey, can I skip this? Square root of 4 is 2. There's multiplication here, so that's 2 times 2, which is 4 root 3. Okay, that's one reality. Now let's look at a separate reality, and I'll change the color so we can refer to the blue and the red. Okay, say I had square root of 48 and times the square root of n to the fifth. Okay, the thing is that the perfect square factors, we usually go through them from least to greatest. 0, 1, 4, right? Then 9, because 3 squared. 16, which is 4 squared. 25, okay, etc., etc., etc. The fact is that we actually want the greatest perfect square factor to make our lives as easy as possible. 4 is indeed a factor of 48. But 4 is a factor of 16, so it's possible that 16 is also a factor of 48. In fact, it is a factor of 48, 16 times 3. So this is the alternate reality. Had we done, instead of square root of 4 times 12, we did square root of 16 times 3, we would have had using the product property of square roots, square root of 16 times the square root of 3, and we get 4 root 3. And as you can see, it's just less steps to have to do it this way, and it eliminates the possibility of you going, okay, I'm finished, 2 root 12. No, 12 still has a perfect square factor. Now moving on to the n to the fifth business, and I think we can just do this over here, and I'll just try to do the steps here. Okay, Remember that square roots are really rational exponents in disguise. So this is n to the fifth over 2. And I'm just going to write that way over here so it's not in the way. N to the fifth over 2. Okay. As we discussed in class, we can use the product property, the product of powers property, and we can rewrite this as, well, what number less than 5 is divisible by 2? And the fact is that it's 4. And we can write n to the fifth as n to the fourth times n to the first. This is the product of powers property. So you keep the base, add the exponents. Yep, that's n to the fifth. And now we can again use the product property of square roots. And we get square root of n to the fourth times the square root of n to the first. And look at that. That's just going to be n squared, right? Because this is going to be 4 over 2. Instead of 5 over 2 like we had earlier, this is 4 over 2. 4 divided by 2 is 2. Also, if you think about it, n squared times n squared would be n to the fourth power because you'd add the exponents. But we still have this times square root of n business going on over here. Okay, now look at this mess. Blech. Well, using commutative property of multiplication, we can put the factors which are not in square roots next to each other. So that's 4n squared. That looks a little nicer. And then if you have a square root of 3 times the square root of n, you can use the product property of square roots to put those under the same radical. So the radicand becomes 3n. And this is indeed as simple as the square root of 48 n to the fifth can be. I always find it interesting for students who are having trouble. Here's a little technique I use. If you take 4 and you want to put it back in the square root, you're going to have to square it. So 4 squared is 16. That 16 would go back under the square root, and you'd have 16 times 3, which is 48. If you square n squared, that's n to the fourth. You put that in here, you have n to the fourth times n, that's n to the fifth. So it's a little technique you can use. Whatever's outside that radical, you can square it and put it back in to make sure that you get the original expression. Okay, that's it for number 20. I'm going to now go on to, I believe it's number 59, and my computer's going really slowly. Kind of like you guys probably are right now. You just woke up. You're like, this ain't so bad. Okay. These problems, please read the directions. Write a factor that you can use to rationalize the denominator. They're not asking you to rationalize it. They're asking you, what is the factor? What is this? What is this fraction you're going to use? It's square root of 6 over square root of 6. Shh, don't tell anybody. But that's all they want here, and the same goes for this. And of course, you'll be using conjugates because you have two terms in the denominator. Okay. 59, I believe, was the next problem that I was going to do. Aye, Captain. Okay, so simplify 3 over the square root of 5 minus the square root of 2. Oh no, are those square roots in the denominator? Ah! Okay, we need to get rid of them. We can't have them there. They're causing too much trouble, Captain. As I said in the last video, we were thinking of this as A minus B. And we're going to use our special product pattern with binomials, a minus b times the quantity a plus b. And we're going to use this to our advantage. This is a squared minus b squared, the difference of squares, right? We're going to use that to our advantage here. And I guess I'll just work sideways with a ton of equal signs. Okay, I have to multiply by 1 because after all, this is an expression. It's not an equation. I can't just do what I want to both sides. There are no two sides. So I need to multiply by 1. And the way I'm going to do that is I'm going to multiply by the same value in the numerator as the denominator. This is a minus b. I want a plus b, better known as the conjugate. And you get this. Oh, yeah, it's so beautiful. Oh, look at the beautiful math. Square root of 5. Ay, Abuka, ¿por qué no estás haciendo? Ay, oh, there it is. Plus. Oh, man, this is so hard, guys. I need to go back to school and get a master's degree in this. Okay, so we're multiplying by 1. We're not changing the value of this expression. Beautiful, beautiful. Why do we multiply by the conjugate? Square root of 5 plus square root of 2. The conjugate of square root of 5 minus square root of 2. Because we get a squared minus b squared. Well, guess what? Hold on, that line was terrible. Now the pressure's on to do this better. Oh, it's not that much better. Okay, so we're going to square both of those. What's the square of a square root? Whatever's in the radicand. 5. Minus, okay. Well, we're going to square the square root of 2. That's going to be 2. Beautiful. Now we have 3 times this quantity, square root of 5 plus the square root of 2. This is a factor that's composed of more than one term. Terms are separated by addition and subtraction. We're going to distribute that. Oh yeah, I was going to do the arrows, but there's just no chance I'm going to make those without errors. So we get 3. Well, I guess I could have done this a different way, but I'm going to do it this way. 3 square root of 5 plus 3 square root of 2. Okay? And you get to here, and you do this, and you go, all right, and you go, oh, babe, this is amazing. What beautiful math. You get this, and you turn into Big Ideas, and Big Idea says, no! That is incorrect! After all, we are simplifying. Okay. It's so crucial that you guys remember to distribute here. It really is. And I'm glad that we just went over it. However, in this particular case, it may have been better if we hadn't, so you saw something really important. Had we not distributed, and we could go back from distributing by factoring out the 3, we had this. And the reason this is interesting is because this, the 3's cross cancel. Now when I say cross cancel, here's why they cross cancel. When you have 2 factors up here, you can think of those as fractions being multiplied together. So this is 3 times, and then we'll still keep this in a quantity, okay? Square root of 5 plus the square root of 2, all over 3. Okay, if multiply 3 times the square root of 5, quantity 3 times the quantity square root of 5 plus the square root of 2, that's this, right? And 1 times 3 would be 3 in the denominator. The 3's cross cancel or cross reduce, which is really what they're doing. The greatest common factor of 3 is 3. You divide both 3's by 3, you get 1. And you just get the square root of 5 plus the square root of 2. So it's those other algebraic tricks that go way back to when we were dealing with cross-canceling and factoring out and all that other stuff that we've learned way back in Math 6 Accelerated. It's the same stuff that you have to apply here to make sure you get this entirely simplified. All right, everybody, as always, go on to Google Classroom. If you have more questions, you can ask those questions there. I'll be checking those throughout the school day. You guys are all amazing. I miss having you in class, but I'm glad that we get to hang out via the interwebs. So stay safe. Have fun.